Okay, 3, 2, 1, it's jam.
What's up, science fam? By now you should know that all matter in the universe is made of atoms. But then, what are atoms themselves made of? And how do these components of atoms contribute to their properties? That's what we're going to talk about in this session. My name is Sir Ramon, and this is Science with Sir Ramon. The atomic structure and electron configuration is our topic for this session, and what we're planning to do is to be able to tell how many protons, neutrons, and electrons are in a particular atom, describe the electron configuration of given elements and ions, determine the quantum numbers of an electron, and relate these quantum numbers to the properties of an electron based on the quantum mechanical model. All of this sounds very complicated, but we'll go through this together. So you thought that the atom is the smallest unit of matter, but no, it's not. The subatomic particles of an atom are actually, still forms of matter. So these subatomic particles are the electrons, protons, and neutrons. The electrons were, of course, discovered by J.J. Thomson, discussed in another video regarding the history of the atomic model. So J.J. Thomson figured out that electrons, or negatively charged particles, exist in atoms. On the other hand, protons were discovered or credited to Ernest Rutherford thanks to his pew-pew laser experiment with gold foil. And neutrons were credited to James Chadwick because he realized that protons can't stay together unless there's something else that's with them in the nucleus of your atom. So, regarding that, what exactly keeps the nucleus together? Your protons, being positively charged, would repel each other really strong. They don't want to be next to each other. So how then can we have a positively charged nucleus? So what happens is that your neutrons play a key part in keeping the nucleus together. So your neutrons and your protons together in the nucleus exhibit strong nuclear force. This is a fundamental force of nature. So it holds the nucleus together by exchanging fundamental particles, much more basic than your neutrons and protons. So when these neutrons and protons are too close to each other, they start exchanging fundamental particles that keep the nucleus together with a strong nuclear force. Think of it as like magnets, except electromagnetism is a much weaker force than the strong nuclear force, like a super magnet that only works with protons and neutrons. So your protons, your positively charged particles, and your neutrons, your neutral particles, when they're together in the nucleus, they hold each other together because they're made of quarks that can exchange with each other in your nucleus when it's in that small of a distance with each other. So the smallest particles in an atom are actually electrons, and the quarks, again, your protons and neutrons, are made of these quarks. Alright? So electrons in particular have unique properties. Those tiny things that orbit around your atom, they have unique properties that can be described using quantum numbers. So these quantum numbers, there are 4 of them, and we'll talk about them one at a time. But there are 2 ways to describe the quantum numbers of an electron. We have the electron configuration, which functions like a quick summary of the quantum numbers of the electrons of a single atom, while the orbital diagram is a more complete but tedious way to show all these quantum numbers for each electron. So we're going to talk about the quantum numbers first. So these are the 4 quantum numbers. Listed above me, we have the principal number, which describes the energy of an electron, so how much energy it has. So if your electron, which orbits around an atom, has a lot of energy, it will tend to have a very wide orbit. If it has very small amounts of energy, that electron will have tiny orbits. So the principal number, or n, describes also basically the size of the orbit of your electron. The next quantum number is what we call the azimuthal quantum number, symbolized by a fancy L. So it describes the angle or shape of the orbit. So if you look at our example here, there are multiple shapes that you can see in our quantum mechanical model. There's a sphere, there's some shapes that look like a dumbbell, and then there are other shapes that we'll only be able to see in more complex atoms. So the azimuthal number is just describing what exactly is that shape. It's not just a sphere. Sometimes it can be a different shape. Your magnetic number, symbolized by the letter M, and the fancy L of the azimuthal number, describes the orientation in space of your electron's orbit. So we'll talk more about that later when we go through these one by one. And your spin number, the very last quantum number, is symbolized by M and the fancy S, which describes the spin of your electron. So your electrons spin while they orbit, and that spin number describes how they spin. So let's discuss these one by one so we can discuss them with more detail. Again, the principal number describes the energy or the size of the orbital. So more energy means a wider orbit, and when we talk about electron configuration, it's always the first big number used to describe the electron configuration. So this first large number here, the number 1, that is the principal number when we're talking about electron configuration. More on that later. Next is the azimuthal number. Again, this describes the angle or the shape of the orbit, and it's called a number based on this numbering system of 0, 1, 2, and 3. But these numbers, 0, 1, 2, and 3, correspond to different letters, which also correspond to different shapes. So S stands for sphere. P, these are complicated terms already, the P, D, and F shapes. So let's just keep them with their letters, P, D, and F. So P looks kind of like a dumbbell, like a weird dumbbell. D is like a clover, and F is like one of those weird party animal balloons that clowns make. In other words, S is the simplest, and F is the most complex shape. And each of these shapes, again, correspond to a specific azimuthal number, with S being 0, P being 1, D being 2, and F being 3. Now, in an electron configuration, it's written as S, P, D, or F to remove some of the confusion if we use these numbers that were used before. So in this case, the same example as earlier, that S means that the orbit of these electrons is in the shape of a sphere. And that's also corresponding to its azimuthal number, which is 0. Don't forget how the shape, how the letters correspond to the numbers for the azimuthal. So next concept is that the principal number, the energy level, limits the possible azimuthal number, or limits the possible shape. So it just makes sense. The less energy you have, the less possible shapes you can have for your electron's orbit. So in this case, we can see in this table here, for principal quantum number 1, we only have one possible shape, which is the S shape. For principal quantum number 2, we have two possible shapes. So you have the introduction of your P shape. For 3, we have the D shape. For 4, we have the F shape. Theoretically, there might be G, H, I, J shapes, but in nature, we've only been able to prove up to the F shape, or the F azimuthal. Next, we have the magnetic number. This describes the spatial orientation, or how it's flipped around in space, your orbit of the electron. So if the azimuthal is the shape itself, the magnetic number describes how that shape is oriented in space. So if we zoom in on these examples here, for example, your P orbital. So your P orbital in this second row. So there's 3 possible orientations in space. It can be horizontal, it can be vertical, it can be going diagonal in 3D space, at least for the P shape. And for the more complicated shapes, your D shape and your F shape, they get even more complex, to the point where it's very difficult to describe them already. But the main point is that the possible magnetic numbers, or the possible orientations in space, are actually in a regular series. So for S shape, there's only one possible orientation in space, which is, it's a sphere. No matter how you manipulate the sphere, it's just a freaking sphere. So the magnetic number that's possible for the sphere is just one number, which is 0. For your P shape, since there's 3 possible numbers, again, in your orientation in space, it can be vertical, it can be horizontal, or it can be diagonal, or coming out of the page. So those 3 possible numbers become 0, -1, and 1. Think of it as a number line. It spreads out from 0. For your D shape, there's 5 possible orientations. So the numbers that are possible are -2, -1, 0, 1, and 2. And finally, for your F shape, there's 7 possible numbers. So we can go from +3 to -3, along with a 0 magnetic number. All right. So like the magnetic number is like a label or a name for the spatial orientation. And it always starts with the middle, which is the 0 number. So that's why we have 0, 1, -1, 0, 2, -2, and so on for your S, P, D, and F azimuthal numbers. And finally, we have the spin quantum number, which sort of describes the electron spin. It's a bit more complicated than that, but we won't go into detail. It's just called intrinsic angular momentum. It's sort of like spinning. So it's represented as either half integers, like positive or -1/2, or as arrows, up or down arrows. And this is a direct result of what we call Pauli's exclusion principle. We'll talk about it in a bit. Their magnetic and spin quantum numbers are only shown using the orbital diagram. That's why the electron configuration, which you can usually find in some of the more modern periodic tables, are considered summaries because they don't show the magnetic and spin quantum numbers. All right, so in Pauli's exclusion principle, again, the thing that that allowed us to be able to say there's only an up and a down spin for your electrons, it just states that electrons in an atom can't have the same 4 quantum numbers. So if you have one atom, all of those electrons have different combinations of quantum numbers, different combinations of those 4 quantum numbers. They're like they're like car licenses. Okay? They're like license plates. You can't have the same license plates on different cars. All right. So in Pauli's exclusion principle, if we apply it to orbital diagram, you can't have the same spin in each box because that means that there are electrons with the exact same quantum numbers because each box has the same principle, azimuthal and magnetic quantum number. The spin is the arrow, so they have to be opposite arrows so that they would always have different sets of quantum numbers. Basically, we can just degenerate this, we can simplify this into the idea that there's only 2 electrons in an orbital and they must always have an opposite spin. Now, to clarify some terms that we're using, the orbital in the orbital diagram is the box, the individual boxes. A shell are boxes in the same level, meaning all the boxes in the same principal number. A subshell is a series of connected boxes, and the magnetic number is just the name or the label for each of those boxes. Next, we're going to talk about the electron configuration and orbital diagram. So again, the electron configuration is a summary, while the orbital diagram is the more complex way of describing the quantum numbers. Now, here we have an electron configuration example. This shows us what numbers we can see in an electron configuration. So we have the principal number, the big number here, the azimuthal number, the letter, and for the magnetic and spin quantum numbers, they are summarized in a way by the exponent or the superscript number, which actually just describes the number of electrons in that orbital or in this box, right? So if we convert this into an orbital diagram, we get this. On the side over here, this is the box, this is the orbital. We have the single electron with the up arrow. So this one electron is symbolized as an up arrow to show the spin of that electron. So these are basically equivalent ways to describe. So 1s1 is the same as this diagram, which is the box and the up arrow. They both communicate the same things, the 4 quantum numbers. All right. So moving on, again, it's kind of complicated, but let's do this step by step. Okay. So first, let's see how to get the electron configuration of an atom. First step is to get the number of electrons in the atom. So let's start with that. When we're talking about an atom, to get the number of electrons for neutral atoms, we just refer usually to a periodic table. The atomic number, the number usually at the top left or the top of your atomic symbol, is also the number of electrons because that number is actually referring to your number of protons, which are positive. So if you have a certain number of protons, in order for it to be neutral, you need to have the same number of electrons. In other words, your atomic number will be your number of electrons in neutral atoms. But if your atoms have charges, if they're ions, then your atomic number has to be adjusted minus the charge. So if we have positive 3, then 13 minus 3, the number of electrons it has is 13 minus 3, or 10 electrons. So don't forget, it's the atomic number minus the charge. Take note that the charge can be negative as well. So a negative charge would be, for example, chlorine with a charge of -1. So if we have chlorine with a charge of -1, we'll take its atomic number minus -1, which will cancel out to become +1. Right? So don't forget your integers in your math classes. Next step, once you have the number of electrons in the atom, is to fill the orbitals in order of the Offbow principle. This sounds complicated, but this is easier with pictures. So what is the Offbow principle? Offbow is just a complicated term, a German term if I'm not mistaken, for building up. So it's a term for building up the principle that by which we build up the electron configuration. It's the order of what's easiest to fill. So the rules are, the lower energy levels get filled first. So your n is equal to 1, usually they get filled first. And the second rule is that simpler shapes also get filled first. So S will get filled before P, before D, and before F. But there are exceptions that begin at the orbital 3p. And your Offbow principle is usually shown in a diagram like the one on the left. There's usually your written as in different levels. So you have your n is equal to 1 and n is equal to 2. You write them down all in organized rows and columns. And then your Offbow principle, you just diagram it by having diagonal arrows. So you go through 1s, then 2s, then 2p and 3s. Then at 3p, see, normally if we follow these rules 1 and 2, after 3p, we should proceed to 3d. It's the next simplest shape in the lowest energy level. But because of the Offbow principle, because there's exceptions that start at 3p, we go skip 3d and we go from 3p going to 4s. We follow the arrow, we follow the diagonal line. All right, the reason for this is because at higher energy levels, the simpler shapes start becoming easier to fill. So even though 4s has higher energy level than 3d, the S shape, the spherical shape, is much simpler than your D shape. That's why we go for the 4s orbital first. All right, so again, we're going to keep this diagram on screen while we do some of our examples. So the third step is to keep going, keep filling the orbitals until you reach the same number of electrons in the atom. So let's take some of the examples later on. All right, so if we just translate this to an orbital diagram, we have these boxes. So in your S shape, we only have one box. This is equivalent to your maximum number of magnetic quantum numbers. Just remember that your S shape can have one box, your P shape can have 3 boxes, D can have 5, and F can have 7. So that also corresponds to the total number of electrons you can have in each orbital. So for S orbitals, you can have 2 electrons, P orbitals can have 6 in total, D can have 10, and F can have 14. And these numbers here are just the corresponding magnetic quantum numbers that we can have. So simplifying this, if we put the max number of electrons for each orbital, we should have 2 electrons for S, 6 electrons for P, 10 electrons for D, and 14 electrons for F orbitals, no matter what energy level it is. And we only have partially filled orbitals. We only have numbers of electrons less than these if it's the last orbital before getting to the number of electrons that the atom has. All right, so this is very complex, sounds very complex, but again, this is much simpler with pictures and examples. Let's start with a rather simple element. We'll start with carbon. Carbon has an atomic number of 6. So the neutral carbon has 6 electrons. That's step 1. We're done with step 1. 6 electrons. So next we do step 2. We follow the Offbow principle. We fill in these orbitals based on the Offbow principle. So we start filling at 1s, the most simple one at the top left. 1s. And again, the S shape can only have two, maximum of 2 electrons. We write 1s2. So that's filled. We go to the next orbital after 1s, and according to the Offbow principle diagram here, the next one will be 2s. So we fill that up as well. Again, the S shape can only have 2, so 2s2. So we have 2 electrons in 1s, 2 electrons in 2s, that's 4 in total. 2 plus 2 is 4. So we only have 2 electrons left. So when we go to 2p, based on this diagram here, if we go to 2p here, we just fill in 2. So 2p2. Instead of writing 2p6, we write 2p2 because there's only 2 electrons left to get the total of 6 electrons. If we add all of these superscript numbers, we have 2 plus 2 plus 2. We have 6 electrons in total. So take note that your p orbitals again can take 6 electrons, but we can't skip the orbitals that come before it. We can't just say, okay, there's 6 electrons, let's just shove them all into 2p. We can't do that because we have to follow the Offbow principle. We have to fill in 1s and 2s first. So what about a bigger atom? Let's try a bigger atom so we can see the exceptions to the Offbow principle. So this is tin. Tin has 50 electrons. So if there's 50 electrons, we'll have to have a much longer electron configuration. Again, we're still following this the Offbow principle in this diagram here. So again, we start with 1s, then 2s, then 2p. We keep going. So 1s2, 2s2, 2p6. If we add all of that, 2 plus 2 is 4. 4 plus 6 is 10. So this is just 10. We have 50 electrons, so we have to keep going. 3s2, 3p6, and again, 3p is when we have exceptions in our normal order. So if we refer to our diagram here, after 3p, we go to 4s. So we fill in 4s2. After 4s2, we go to 3d. So we can finally fill 3d. So we fill in 3d10. After 3d, if we follow the diagonal arrows, we have 4p, then 5s. So we put 4p6, 5s2, and we keep following this diagram, 4d10, and then 5p2. Why did we stop at 5p2? Why not 5p6? Because we reached 50 electrons. This is 10 electrons up to 2p6. We have another 10 until 4s2. We have another 10 in 3d10. So we have 40. We have 30. We have 8 in 5p6 and 5s2. We have 4d10, so that's another 10. 10 plus 8 is 18. So we have 48. And finally, the last 2 electrons in 5p2. So again, after 3p, the simpler shapes are easier to fill. That's why the order seems like it got jumbled up. We have 4, then 3, then 4, then 5, then 4, then 5. That's again because of the Offbow principle. Again, in this kind of diagram. Make sure that you have your Offbow principle diagram. If in the future in our online quizzes, we'll have the diagram in your quizzes, or you'll be asked to search for it in Google, or you can write it down manually in your written exams by just writing down the different orbitals in order. So again, 1s, 2s, 2p. So again, different principal numbers should be in different rows, and your different azimuthal numbers or different shape letters should be in different columns. And then you just add your diagonal lines. So how about orbital diagrams? How do we make orbital diagrams? The more complex way of describing the quantum numbers. We have Hund's rule first. You have to follow Hund's rule. So Hund's rule basically states that it's easier to fill a subshell with one arrow in each box first. So another simple way to simplify this is to think of your orbitals as hotel rooms. So if you think of it like a hotel, you get more money from having guests in each hotel room than letting the guests share. So you'll want the guests to occupy different rooms first before you start letting them share rooms. So in this case, for example, it's correct to have one arrow each in your 2p orbital rather than to shove 2 arrows into one box. So that's Hund's rule. We have to distribute your arrows in one box each first, or one arrow for each box first. And it only applies to connected boxes or subshells. That's why for this example, we still have paired up 1s and 2s. So 1s and 2s still have pairs of electrons because they're in different subshells. They're like in different hotel room floors. Okay, so your each hotel room floor or each subshell is the one that follows Hund's rule. So one arrow for each box first before you start pairing them up. The second rule, which we actually already discussed, is Paulies' exclusion principle. You can't have the same type of arrow in each box. Again, if it's a hotel room, you can't have the same types of people in the hotel room. So only people of opposite types in the hotel room can pair up. It's kind of weird. So again, they must have opposite spin. So how does that apply to your orbital diagram? So going back to one of our examples, carbon. So carbon, again, we have its electron configuration. If we turn it into an orbital diagram, these are the basic steps. First, we draw and label the boxes. So we draw the boxes, and the boxes correspond to your azimuthal number or your letters. So for S azimuthal or S shells, you only have one box. So we just draw one box. Let's label that box 1S. Your 2S, again, a different energy level, but still the same shape, will only have one box as well. So we label it 2S, and we only have one box. For your P orbital, so for your P, there's 3 possible boxes. Again, S has 1, P has 3, D has 5, and F has 7. So your P orbital will have 3 boxes available. Then next step for your orbital diagram is to add the arrows. So that's again based on your electron configuration or based on the number of arrows in your carbon. So again, following Hund's rule and Pauli's exclusion principle, if we start with 1s, let's put an up arrow first. Again, Hund's rule says up arrow first. So up arrow, then down arrow. That's your 1s2. We have the 2 electrons here. Same for 2s2, your 2 electrons, opposite spin, up arrow first. And for your 2p, again, we have 2 electrons. Again, based on Hund's rule, we fill it up with up arrows first for each box. So 1 and then 2. So we no longer have to add any more arrows because that's your 2 electrons right here. And if we add all the arrows together, 1, 2, 3, 4, 5, 6, we have these 6 electrons of carbon already. So this is it. This is the orbital diagram of carbon. Very simple. What about for tin, the 50 electron one? So if it has 50 electrons, of course, it has many more boxes. But same thing, we have to follow Hund's rule and Pauli's exclusion principle. Again, Hund's rule just means that we put up arrows first. So all of these had their up arrows put in first. Again, at the final orbital 5p2, we have 2 electrons. So we put the up arrows first. 1 up arrow per box first. So 1, 2. Again, there's only 2 electrons. So we stop there. That's why 5p2 looks like this. Every other orbital is completely filled. So we just write down all the appropriate numbers of boxes for the shapes. Again, for S shapes, we have 1 box. For P shapes, we have 3 boxes. For D shapes, we have 5 boxes. And so on. Alright, so again, in your orbital diagram, it shows you the different quantum numbers. For example, let's focus on the last electron of your tin. So the last electron that we put into our orbital diagram is over here, this one. So we can identify the 4 quantum numbers based on this orbital diagram. First quantum number is 5, second quantum number is P. Or in terms of the number itself, S is 0, P is 1. So azimuthal number is 1. Your magnetic quantum number is the label of the box. Again, for P orbitals, for magnetic quantum numbers, we start labeling the boxes based on the middle, which is 0. So this middle box is 0. The one on the left is -1. The one on the right is +1. So it's in box 0. So its magnetic quantum number is 0, and its quantum number for spin is the upwards quantum number, which is +1/2. So again, your quantum numbers can be summarized by your orbital diagram. Oops. All right. So is there a shortcut for this? This is horribly complicated, sir. What's the shortcut? The periodic table actually is arranged in a way that you can tell what is the electron configuration of an atom based on where it is in the periodic table. So the elements are actually arranged in blocks of the same azimuthal, or the same orbital shaped blocks. We have the S block here, the P block here, the D block, and the F block. So you can know if the last filled orbital has an S, P, D, or F shape. So what about the principal quantum number? That's actually symbolized by each period or row in your periodic table. So the first row is principal number 1, second row is principal number 2, and so on. 3, 4, 5, 6, 7. And your F block is actually inserted here. In most periodic tables, they show that it's supposed to be inserted here. All right. Next, your valence electrons, or your number of electrons in the outermost energy level, is actually indicated by the group numbers on top. So this has one valence electron, or one electron in the outermost energy level. This has two in the outermost energy level, and so on. So even the smallest things, your atoms, your subatomic particles, they can be quite complex and unique. So no matter how small you feel, just remember, electrons, if they can be as complex as having so many quantum numbers to describe each and every one of them, you yourself can be unique. You yourself can be even more complex. That's pretty much it for this topic. I'll see you guys next time.
That is over.